In this lecture, we are going to discuss some examples in the computation of the distribution factors for bridges. For example number 1, we are given a pre-stressed precast girder bridge in which we are going to solve for the live load distribution. So take note that for a pre-stressed concrete precast girder bridge, this is also an example of a reinforced concrete deck girder bridge. So we're given here the typical section of our bridge. We have your deck, then we have here your supports, we have here your traffic barrier or the parapets. Then we have your span configuration. So it means that for this section, this will be found at each of these support. So we are given the properties of the bridge for the girder. It is designed using the AASHTO type V girder with area 65, 35, 87 square millimeters, moment of inertia 216.9 times 10 raised to 9 millimeters raised to 4. Its height or beam height is 812 millimeters, and the height of the neutral axis is 788 millimeters. We also have the concrete properties. The girder compression strength is equal to 48 megapascal, and the slab compression strength is at 27.5 megapascal. So assumptions will be that the bridge would contain intermediate diaphragms. Okay, so from our given data in our given sections, we can see that this is a 3-span continuous bridge. So we have 3 spans, continuous bridge, since there are supports between our end supports. So for our solution, we first use table 4.6.2.21-1 to identify now the cross-section or typical cross-section of our given bridge. So again, we are given a precast concrete deck that is supported by precast concrete. So in this case, the typical cross-section falls under K. So for our first step, we solve for the longitudinal stiffness parameter, K sub G, in which it is solved using the equation N times the quantity I plus E squared. So for N, that is our modular ratio, which is the ratio of our elasticity or modulus of elasticity of the beam to the slab. We're not given the modulus of elasticity for beam and slab, but we are given the compression strength of the girder and the slab. Therefore, we can solve for the elasticity using the equation 0.043 times the unit weight of concrete raised to 1.5 times the square root of the compression strength. So with this cancels out, leaving us with square root of 48 divided by square root of 27.5, which will give us a value, the modular ratio equal to 1.30. So next, we want a value of I, which is already given in our property. The area is also given as well. So next is to determine E sub G, which is simply the distance between the centers of gravity of our beam and the deck. So in this case, we use this diagram to determine our E sub G. So E sub G now will simply be the sum of our centroidal distance of the beam and the centroidal distance of the slab and of the beam. So that will be given by PS over 2 and Y sub. In this case, E sub G is equal to YT plus 1 half T sub S is equal to 78 millimeters plus 1 half of 240 millimeters, which is now equal to 908 millimeters. So we already have now all the values to solve for K sub G. Substituting these values, K sub G is equal to 1.32 times 216.9 times 10 raised to 9 plus 653587 times 908 squared will give us a value of K sub G equal to 9.976 times 10 raised to 11 millimeter raised to 4. So next step is to solve for the number of your design lanes, in which the design lane N sub L will be computed as the roadway width divided by 3,600 millimeters. So for the number of design lanes, so let's go back to the given section. So the roadway width will simply be the distance from the edge of your barrier or the parapet to the end of the other side of our parapets. So we are given that the distance between the center line of the exterior girder to the end of or edge of your lane or edge of the parapet is 910 millimeters. So this is a symmetrical bridge. So therefore, 910 is the same distance for this side. In that case, the roadway width now will be equal to 10,000 millimeters plus 2 times 910 millimeters. And that is now equal to 11,820. So divide it by 3,600. The number of design lanes now for this given bridge section is 3 lanes. So from there, we now start off with the computation of the moment distribution factor in our interior beams. So to identify our equations for the moment distribution factor, we use table 4.6.2.2.2b-1. So again, from our first table or from the given table, our section is K, or we could also use from the type of structure here without looking on the cross section from table 4.6.2.1-1. We are given a pre-stress concrete slab. So that's an example of reinforced concrete, and it is resting on a precast girder. So it's also a concrete. So it's a reinforced concrete slab, which is a pre-stress concrete, and it is a concrete beam or concrete girder. So therefore, we're going to use now these equations for our distribution factors for one design lane load and two or more design lane load. So with this, we now check for our conditions. So for the moment distribution factor for interior beams, the conditions now is that the number of beams should be greater than or equal to 4. The spacing between the stringers should be within 1,100 millimeters and 4,900 millimeters. The thickness of the slab or the deck should be 110 to 300 millimeters. The length of the span between the supports is 6,000 to 73,000 millimeters, in that your longitudinal stiffness parameter should be ranging from 4 times 10 raised to 9 and 3 times 10 raised to 12. So for the first condition, the number of beams, so you could simply count off the number of stringers in this diagram. Or for example, if the diagram is not complete but is only drawn from 1 and 2, the center line, we could use the given data here, which is 5 spaces at 2,000 millimeters. So what does this mean? There are 5 spaces between your stringers, so 5 spaces. So 1, 2, 3, 4, 5 spaces. So basically, it would mean that we have 1, 2, 3, 4, 5, 6 stringers. Okay. So example again, if for example we do not have a complete section of the bridge and we are given that the bridge is, let's see, 4 spaces at, let's see, 2,500 millimeters. So it means that we have stringer 1, stringer 2, that's 1 space, stringer 3, 2 space, stringer 4, 3 space, and stringer 5, 4 spaces. So meaning 4 spaces will give us NB, which is equal to 5. Okay. So in this problem, we now have NB is equal to, as we have counted, equal to 6. So meaning it's greater than 4, the condition. So the first condition is satisfied. So next we check on our spacing between the stringers. So this will be your S, or the span of stringer. And we are going to use now from the given section, the space is at 200 millimeters. So S now is 2,000 millimeters. It's within our range. So therefore, the second condition is satisfied. So next condition is the condition for your thickness of slab. So from the diagram, we are given the thickness is equal to 240 millimeters. So checking now, it's within the range. So the condition for the thickness of slab satisfies. And then next, we have your length between the supports. So we use this diagram now. So basically, we have 3 spans in the bridge. So we have to check for L1, L2, and L3. So for L1 and L3, they both are equal to 20,000 millimeters. So checking now for the range, it's within 6,000 and 73,000. Therefore, L1 and L3 satisfies the condition. And L2 is equal to 28,000 millimeters. So it's also within the range. So L2 satisfies the condition. Therefore, all our spans are okay with the condition. And then lastly, we have computed for the value of K sub G a while ago, which is now equal to 9.976 times 10 raised to 11 millimeters raised to 4. So it's within the range. So 9 raised to 9 up to raised to 12. So raised to 11 lang tayo. So therefore, all the conditions now for the equations from table 4.6.2.2.2b-1 is satisfied, the condition is satisfied, therefore we could use those equations. So for the moment distribution for our interior beams, we start off first with span 1 and span 3, since the two spans are equal. But if L3 is of different length, different span length, then we are going to solve for the distribution factors for span 1 first, and then span 2, and then span 3. But in this case, since they are equal, we can solve them simultaneously. So let's start with the distribution factor for the moment for one design lane load. So from the table, the equation now is given by this equation, or by the table gives us this equation. So S will simply be the span. So we also have your L. In this case, we are considering span 1 and span 3. So we are going to use this value for L. T sub G is already given, and T sub S is also given. So just substitute the values for the equation, and we are going to arrive at the distribution factor for the moment. So M is moment in the interior beams for one lane loaded is equal to 0.480. So this is not yet our distribution factor because we still have to solve for the distribution factor for two or more design lane loaded. So using the equation from the table, and then same values to be used. S is 2000, L is 20,000, T sub G is 9.976, and T sub S is 240. So substituting now those values, will arrive at the distribution factor for the moment for interior angles at two or more design lane load. And that will give us 0.649. And our unit here will be lanes. Okay, so we now have two values of the distribution factor. So which of this will be used? So we'll be using whichever gives us the highest value. So in this case, what will govern is the distribution factor for the moment of interior beams for two or more design lane loaded. So next we solve for the moment distribution factor for interior beams for span 2. So same process for span 1 and span 3. We'll be solving for the distribution factor for one design lane load using the equation from table 4.6.2.2.2b-1. So in this case, since we are talking about span 2, will have the same given value that we're going to substitute. The only difference will be we are going to use now the span of L2, which is equal to 28,000. Substitute the values in the equation, and we will get now a distribution factor of 0.427 lanes. And then next, we compute for the distribution factor if our bridge is two or more lane loaded. So using again the equation from the table, we just substitute the values of S, Kg, T sub S, and L sub 2 in the equation. We'll arrive at the value for the distribution factor for span 2 for the moment. For interior, two lane loaded is 0.549 lanes. Okay, so again, whichever gives us the highest value of the distribution factor, that will be what will govern in our computation later on. In this case, we have 0.549 distribution factor for span 2 for its interior. The next step is we compute now for the exterior beams. And for exterior beam moment distribution, we use table 4.6.2.2.2D-1. So using this table now, so again, our bridge has a cross-section of K. So therefore, we are going to use this equations for the distribution factor for one design lane loaded or two or more design lanes. So with this, we check your conditions. The condition will depend on d sub e, which is the distance of our exterior web to the face of your parapet or traffic barrier. So in this case, we have this diagram of our section. So we have here your exterior streamer. D sub E will simply be the distance between the exterior stringer, the center line, to the edge of your roadway. Okay, so with that, D sub E is 910 millimeters, which is greater than negative 300 mm and is less than 1,700 mm. So therefore, the condition is okay. Therefore, we could apply the equations for our given bridge. So for the moment distribution for the exterior beams, we start off again with span 1 and span 3 as they are of equal length. So same process, we start off with the distribution factor when our bridge is one design lane loaded. So from the table, we are to solve for the distribution factor using our lever rule. In this case, we can use this diagram to solve for your distribution factor. So in this diagram, the wheel lines represented by P will be placed 1,800 meters apart, and that the design track will be placed as far away from the interior girder as possible to maximize the reaction on our exterior girder. The reaction will be here on the exterior or the very first stringer or girder in our bridge. So the design track may now be positioned transversely on our bridge deck such that the center of any wheel of this exterior wheel is not closer to the edge of the line or edge of the lane about 600 millimeters. Okay. So for English system, this 600 millimeters will be equal to 2 feet. In this case, for metric system, our constant values now will be distance between the wheels is 1,800 millimeters and the distance of the exterior wheel to the edge of the lane is 600 millimeters. So this is the minimum value of this distance. Okay. Then from here, we can now solve for the distance of the other wheel to the center line of your first interior girder using now 2,000 plus 910 minus 600 minus 1,800. So we'll have 500. Okay, so take note, the only constants here are the highlighted values, 1,800 and 600. The other values will vary depending on the given criteria or given design information of the breach. Okay, so with this diagram, the lever rule now is simply applied, and since our condition checks, we can apply this. So the lever rule will simply be using your statics, wherein we sum up the moments about girder, about this girder. We take this moment. So we have now P times 510 plus P times the distance 1,800 plus 510 minus your reaction at the exterior times its distance to the interior or first interior girder. So with this, we can now solve for the value of RE, but this will be in terms of the P value. So we have 1.41. So this is not yet our distribution factor. We have to apply the lane fraction that is carried by our exterior girder. So basically, the exterior girder now will be carrying two values of P, which is opposed by R. In that case, reaction E is divided to the loads of P. So RE, we have solved already as 1.41 P. So divide it by 2P, we get now 0.705. This is not yet our distribution factor, as we have to include the multiple presence factor of one lane, which is equal to 1.2. So therefore, the distribution factor for the moment for exterior beams for one lane loaded is equal to 1.2 times 0.705, giving us a value of 0.846 lanes. So next, for the moment distribution for the exterior beam for span 1 and span 3, move to the two or more design lane loaded. So from the table, the distribution factor for the moments for exterior for two lanes is given by E times the computed distribution factor of the interior beam. In this case, E now is computed by the equation from the table, wherein DE from the diagram or from the given values is equal to 910. So substituting that in the equation, we'll arrive at E equal to 1.095. And what we have computed a while ago for the distribution factor for interior beams for span 1 and span 3, the governing value was 0.649 lanes. So the distribution factor now for the moment for exterior beams for two lanes is equal to E 1.095 times the distribution factor for interior moment is equal to 0.649. That will give us 0.711 lanes. So comparing this to the value of the distribution factor for one lane, we were able to compute a while ago 0.846, which is greater than 0.711. Therefore, the distribution factor for the exterior beam for span 1 and span 3 will be the distribution factor for one lane, which is equal to 0.846. So next, we solve for the moment distribution factor for the exterior beam for span 2. So again, from the table for one design lane load, we'll be solving this through the lever rule. Since we have the same cross-section for or same properties for our cross-section, basically we'll arrive at the same value of the distribution factor, which is 0.846. So with that, we now solve for 2 or more design lane loaded. So we use now same equation, E times the dF of the interior. We're able to solve for E equal to 1.095. So for the distribution factor, for the interior beam for moment for span 2, we're able to solve that the governing value is 0.59. So with this value of E and the interior beam distribution factor, we can now solve for our moment distribution for the exterior beams, and that will give us 0.650 lanes. So again, comparing this to our distribution factor for moment at the interior beam for 2 lanes for span 2, we could see that the distribution of the moment for exterior beams for 1 lane loaded, which is 0.846, is greater than the computed value of 0.650. So therefore, the distribution factor now for the exterior beam at span 2 will be 0.846. So before we move on to the computation of the distribution factors for shear for our interior and exterior beams, we have to check first the moment distribution factor by the rigid method. So take note that for slab on girder bridges that would contain diaphragms, the distribution factor for exterior beams must not be less than that which would be obtained assuming that the cross-section would deflect and rotate as a single rigid unit. So the checking now for the exterior moment distribution factor by rigid method is an additional requirement since the distribution factor equations in table 4.6.2.2 were determined without considering the effects of the diaphragm. In this case, the distribution factor now for the moments at exterior is equal to m times r, wherein m is our multiple presence factor and r is computed by this equation, wherein n sub l is the number of lanes, r is your reaction on the exterior beam in terms of the lane. Then we have E, which is the eccentricity of the design track or the design lane load from the center of the girder or of the beam. Then X is the horizontal distance from the center of gravity of each girder. X exterior is the horizontal distance from the center of gravity of each girders to the exterior girder. And N sub B is the number of beams or number of girders in our breach. So for this problem, we'll have now the following diagram to follow in your computation by rigid method. So for our rigid method, so the edge of our lane width will be 1,500 millimeters from the edge of your design lane. So the design lane will be this one. And then you have your edge of the lane. So since our computed number of lane a while ago is equal to 3, therefore we are going to place 3 design tracks on our bridge, wherein their centers or center lines will be at 1,500. The second vehicle will be having its center line at 3,600. And the third vehicle will have its center line at 3,600. So if, let's see, we have computed a number of lane which is equal to 4. So if NL now is equal to 4, then it means that I will have to add another set of truck wheels or vehicle design wheels 4, wherein its center of line or center line is located 3,600 millimeters. So basically, for rigid method, what we want to remember is that from the edge of your roadway width, you will be measuring 1,500. And from this 1,500, this will be the center line of your first vehicles. And then 3,600 will be our usual lane width. So 3,600 is your lane width. And it simply means that the distance between the center lines of your vehicles will also be at 3,600. Okay? So for rigid method, we'll have to consider all of our lanes. So meaning we are to compute now for one lane, two lanes, and three lanes. So for the first part, we are to consider one lane loaded. So with one lane loaded, our multiple presence factor is equal to 1.2. So our equation for our reaction will be considering only one vehicle. That's for P1. So your reaction now will be equal to this equation. So NL, we are only considering one lane, so that's 1. Total number of beams is 6, as we have counted. So plus your exterior is the distance between the center line of the set of girders to the exterior girder. That's equal to 5,000 millimeters. So for your eccentricity, we only consider one vehicle, that's for P. So therefore, we'll only be considering one value of P, and that will be measured from the center line of the set of girders to the center line of your first truck or design truck. And that's equal now to 3,600 plus 810. So divide this by the value of x, which is the distance of your exterior or your individual girders to the center line of your set. So in here we have, from the center line, we have 1, 2, 3 girders. So we'll have x sub 1, which is equal to 5,000 squared, plus for the second girder, it's x sub 2, which is equal to 3,000, and x sub 3, which is equal to 1,000. So computing now for this, we have first multiply the entire x squared by 2, since this is a symmetrical bridge, so meaning we'll also have the same value of x1 for the stringer, x2 for this, and x3 for the other middle string. Okay, so computing now, r is equal to 0.48. So for rigid method, distribution factor is simply equal to m times r, which will give us a value of 0.57 leads. So this is the distribution factor for the moment for exterior beams if we are one lane loaded. So we have next two lane loaded. So for two lane loaded road, the multi-presence factor is equal to 1. So in this computation, we're going to consider two design tracks on our bridge. So we have P1 and P2. So for your reaction, again, it's equal to N sub L. Since we're considering two lanes, so that's equal to 2. So divide it by the number of beams, which is 6, so plus your exterior X, the distance between the center of the set of girders to the center line of your most exterior beam, and that's equal to 5,000. Summation of E will be having two values of E since we are considering two lanes already. So from there, so E now will be E1, that's the center of the first vehicle to the center of your girder set. That's equal to 3,600 plus 800. And then we have E sub 2, which is the distance between the center line of P sub 2, vehicle 2, to the center line of the girder set. That's equal to 810. So 810 just simply came from 5,000 plus 910 minus 15 minus 3,600. Okay, so 810 is not a constant value. So with that, we divide now the whole of this term by the summation of x squared, wherein x is simply the distance of the center lines of each girders to the center of the girder set. So we'll have now x sub 1, x sub 2, and x sub 3, which are equal to 5,000 squared plus 3,000 squared plus 1,000 squared. Again, we multiply this by 2 since x sub 1 will have the same distance for the other exterior girder since we are symmetrical. So x sub 2 will be the same for the second girder on the other side, and x sub 3 will be the same for the third girder on the opposite side of our bridge. Okay, so with that, computing now for your reaction is equal to 0.706. Distribution factor now by rigid method is m times r, which will give us a value of 0.0706 leads. So this is our distribution factor when we have two lane load. So we have next is three lane loaded. So therefore, the multi-presence now will be 0.85. We are going to consider three vehicles present on our bridge. So we have vehicle 1, vehicle 2, and we have vehicle 3. Okay, so with that, we have now your reaction will be equal to NL. Since we're considering 3 lanes, that will be equal to 3. The number of beams is 6. So plus your exterior is 5,000 times the summation of your eccentricity. So meaning it's the distance between the center line of your set of girders to the center lines of each design trucks or design vehicles. So we'll have E1, E2, and E3. So E1 is 3,600 plus 810. E2 is 810. And E3 is 3,600 minus 810. It is subtracted since E3 is found on the opposite side of your center. So for the X values, we'll still have the same values, X1, X2, X3. And again, this will be multiplied by 2 to consider the other side of your breach. So with that, we'll now solve for a value of 0.674. So again, distribution factor by rigid method is M times R, which will give us a value of 0.573 lanes. And since we have computed an NL equal to 3, therefore we stop at the computation for distribution factor until 3-lane loaded for rigid method. Okay, so we'll not continue with the 4 lanes. But if we have computed an NL equal to 4, then we move on until 4 lanes. So meaning for rigid method, we solve for your distribution factor until the total NL computed with the equation roadway width divided by 3,600. Okay? So kung ang na-compute natin using this equation is, let's say, 6 lanes, then you have to compute for the distribution factor by rigid method until 6 lane loaded. So after checking the moment distribution for exterior beams by rigid method, we can now move on to the computation for the shear distribution factors. So we start off first with the interior beams, in which we're going to take now our equations from table 4.6.2.2 3A-1. So again, our cross-section is type K bridge or a type K cross-section. So meaning we're going to use this equations and conditions. So since in B, number of beams should be greater than or equal to 4 for us to use this set of equations, we have identified a while ago that NB is equal to 6. So therefore, we are going to use now this equation. So ito, lever rule will only be used if we have NB equal to 3. Okay? Next, we check on now with our S condition, the spacing between the stringers. And we have identified that it satisfies our conditions, same as for T sub S, length for L1, L3, and L2 is checked, and for kg, it's also okay. So therefore, we now use the equation for our shear distribution using these equations. So for our shear distribution for interior beams, we will solve for all of our span 1, 2, and 3. For one design lane load, that's equal now to 0.36 plus S divided by 7,600. So unlike for the moment distribution factors, wherein it is affected by the length of the supports or the length between the supports, so kaya tayo nagko-compute ng hiwa-hiwalay. Unlike for this shear, since only the spacing will control your distribution factor, which is a spacing equal to all the spans, then we could compute for the distribution factor for shear simultaneously for all our spans. Again, if the spacing between the stringers will vary between each span, then you have to compute for the distribution factor for shear separately for each spans given. Okay, so in this case, since our S is constant for all values or all of the span length, then we'll solve for one value for all span 1, 2, and 3. So with that, substituting now S in the equation, we now get 0.623 leads. And then for your 2 or more design lane load, the given equation from the table is this one. So it's still governed by the spacing of the stringers. So it's the same for span 1, 2, and 3. So substituting now S equal to 2000, then we'll get a value of 0.721 leads. So again, whichever value gives us the higher value of distribution, that will be the governing value for the shear distribution factor for our interior beams. So next, we move on to our exterior beams, which will be taken from table 4.6.2.2.3b-1. Again, we have our cross-section K. So NB is 6, therefore, ito ang gagamiting equation. Okay? So with that, let's check the condition. DE is equal to 910. So therefore, we are okay to use the equations for the shear distribution factor for exterior beams. So we now move on to the shear distribution factor for exterior beams for all spans 1, 2, and 3. For one design lane load, we'll be solving it again from the table by lever rule. So since no change in our bridge section properties over the spans and over the exterior beams, so it's the same for interior beams, then we will also arrive at the same value of the distribution factor, which is 0.846. So same value we have computed a while ago using the same method, lever rule. Okay, so next we move on to 2 or more design lane loaded. So that's equal to E times DF, or the distribution factor for shear for the interior beam. So for E, we are given from the table equal to 0.6 plus DE over 300, and we know already that DE is equal to 910, which will give us a value of E equal to 0.903. So for our computed distribution factor for shear for interior beams, governing value was 0.721. So E times interior distribution for shear will give us a value of 0.651 leads. So compare again this value to our one design lane load. So this is lesser compared to the distribution factor of the shear for exterior one lane loaded. So therefore, what controls our shear distribution for exterior beams is 0.846. So again, since our given bridge has a diaphragm, so we again check for the distribution factor for rigid or bi-rigid method. And we are checking it for both shear and moment. So we have checked already for the moment a while ago. So for shear, one lane loaded, we get 0.578. Two lane loaded, we get 0.0706. 3-lane loaded, we get 0.573, which are also the same with distribution factors for our moments. So ito yung nakuha natin sa moment kanina. They are the same with the value for shear by rigid method. Since the properties of our cross sections does not change all throughout the entire span of our bridge. So with this, we could now summarize all our distribution factors computed, and the computed values are the distribution factor for strength, service, and extreme event limit states. So for your interior beams, we have your shear value per span for 1 lane and 2 or more lane loaded. We have controlling value for the shear for all spans is 0.721. Then for the moment for all the span, we have your 1 lane and 2 lanes loaded, and controlling values for each spans are this value for the moment. Then for exterior beams, we have controlling value for the shear for exterior for all spans is this value, and for the moment we have controlling value or governing value for the distribution for moment at exterior beams is 0.846. And then by rigid method, we were also able to solve for the shear and moment distribution factors for 1 lane, 2 lane, and 3 lanes. So next, we now compute for the live load distribution for fatigue limit states. So for fatigue limit states, we'll only be using distribution factor computed from your service and strength limit states, which is for one design lane load. And with that, whichever value of the distribution factor for one design lane load, will be dividing it by 1.2. Divide it by 1.2, and that will now be your distribution factor for fatigue. So for interior beams, for shear, this is taken as 0.623 divided by 1.2. So for moment of span 1 and span 3, for interior beam, the fatigue limit is taken as 0.649 divided by 1.2, which is equal to 0.4. And then for span 3, this is the value when we divide it by 0.35. Then for exterior beams, we'll have the same value for 1 lane loaded for shear and moment. So that is 0.846 divided by 1.2, giving us 0.7. So rigid method, you just use the value for 1 lane, which is 0.578 divided by 1, which will give you 0.482. Okay, so that is now your examples on the computation of the distribution factors for bridges. Thank you for